All right, so we'll do the second half here of exam 3, starting on question 15 where we left off. Actually, let's stop that and we'll go back to the whiteboard. So we have a mixture here, and specifically what we have in this instance is a mixture of HCl and acetic acid, or what we have is a strong acid and a weak acid. And when we have a mixture of a strong acid and a weak acid, the strong acid is going to contribute far more to the hydronium ion concentration than the weak acid. So really, we can just disregard the weak acid. Whatever the concentration of the strong acid is, this is monoprotic, so it's going to produce the same concentration of hydronium ion, and I can just take the negative log of the hydronium ion concentration and get the pH. Different concentrations of HCl depending on what version you had, but whatever it is, you just take the negative log of that, and that's going to give you what the pH is in that instance. Next question, we have a buffer again. So we have a mixture of a formic acid, I believe it is, buffer, and the form of sodium formate or the formate ion. No, come on. So the pKa we know for this is 3.74 for formic acid. And we're told the pH is equal to 3.59. So that means if our equation is pH equals pKa plus log of the base concentration over the acid, then if this is 3.74, that means that log portion here has to be equal to negative 0.15, which means to get the negative value from the log, the value has to be less than 1. So that means the concentration of base would have to be less than the concentration of acid, or in this case, the way it's written on here, the concentration of the formic acid must be greater than the concentration. I think it does the whole thing, the sodium formate, but what we're looking at is just that formate ion, the conjugate base there. And not a great deal larger, but a little bit. What would that be? Yeah, 0.7. So we've got 0.7 times as much base as we do acid. So a little bit more acid than base, but not a lot. Get to that one right there. So our next one now is the molar solubility for aluminum hydroxide. So when that solid dissolves in water and dissociates, we should get that. 0 starting concentration of each of these, produce X of that, and 3X of this. So that means our KSP will be equal to X times 3X cubed. Our KSP is 1.3 times 10 to the negative 33. That's equal to 3X cubed is 27, x cubed times x, we should get 27x to the fourth. So divide both sides by 27 and take the fourth root of that, or you can do square root twice. So 1.3 e to the negative 33 divided by 27 and square root, and that should give us 2.6 times 10 to the negative 9 as my value for x. The relationship of x, or aluminum, back to aluminum hydroxide, is 1 to 1. So whatever the concentration of x is, that should also be the molar solubility for the entire compound, the aluminum hydroxide. Quick way to clear the whole thing. Okay. Oh, there we go. All right, awesome. Next one, calculate the concentration of bicarbonate ion in a carbonic acid solution. So we've got carbonic acid. Now this is a diprotic acid. The first protonation looks like this. We may need to consider the second ionization for the carbonate concentration or bicarbonate concentration reducing, except the second ionization is much smaller than the first. So we're only going to deal with the first in this instance, because the second one is going to probably produce a or negligible change essentially. So we start with 0.05 here, 0 and 0, minus x plus x plus x, 0.05 minus x, x and x, the Ka. 1 is 4.3 times 10 to the negative 7. That's going to be equal to x squared over 0.05 minus x, and we're going to do the x is small approximation. So 4.3 times 10 to the negative 7 times 0.05 equals x squared. Take the square root of that, and x is going to be equal to 1.4. Times 10 to the negative 4, which is also our bicarbonate ion concentration. So the answer A, 1.5 times 10 to the negative 4 for that one. Identify the weak diprotic acid. So diprotic means it has 2 acidic hydrogens. There's only 2 options on here that have 2 acidic hydrogens, H2SO4 and H2SO3. So you have sulfuric acid and sulfurous acid. Remember that this is a strong acid, so that then isn't one of our 6 strong acids, and it's diprotic, so it's not one of the strong acids, it must be weak. So that's our weak diprotic acid in this instance. And then lastly, adding which salt will increase the solubility of cobalt 2 sulfide. So I have cobalt 2 sulfide. As that dissolves and dissociates in water, we're going to get this. So what I'd want is to increase the solubility. So I want to be able to dissolve more cobalt and sulfide, increase the concentrations of these in the water. So what I want to do is shift the reaction to the right. And the way I'm going to do that in this case, since this is a solid, it's not involved in the equilibrium expression. The only thing I could do is remove products from the reaction. So sodium sulfide, adding sodium sulfide isn't going to do that because it's got a common ion with the sulfide. So that's actually going to increase the concentration of sulfide. That would decrease the solubility. For cobalt carbonate, same thing. They have a common ion, in this case, cobalt, increasing the cobalt concentration. That's going to push the reaction to the left. That's going to decrease the solubility. NaCl, does not have anything involved in this reaction. So it's neither going to probably increase or decrease the solubility. We won't really see a change. Cobalt chloride, again, common ion there, the cobalt, that's going to decrease the solubility or push it to the left. But the sodium cyanide, or thiocyanate, sorry, has this thiocyanate ion present. And if you look, there is a KF for cobalt thiocyanate or tetrathiocyanate. That has a large K sub F for formation constant. It's about 1,000. So that means if we add sodium thiocyanate, we'll get that thiocyanate ion, which will complex with the cobalt, which will remove the CO2 plus from the solution. So we're removing a product, and that's going to pull the reaction to the right. So that's why the sodium thiocyanate would be the thing based on those KF values. What are the KFs? The other one was cobalt ammonia, cobalt and ammonia, hexaammonia, but it's not one of the options here. None of the salts we had ammonia in it. So even though that would complex, it's not an option. So the only one we know would form a complex out of the ones we were given is that sodium thiocyanate. So that's everything here. Again, if you have any questions, let me know. I added 5 points actually to everyone's score because some people, I guess, didn't know the purple and red, or red and blue make purple, or they don't know about the color wheel or whatever. So I guess just in case, because of that, I just added 5 points to everyone's score. So if you got a 95, or you think, hey, I definitely got one of these wrong, I got a 95, but you see 100, that's why. Or if you got a 70, or you thought you got a 70, but you see 75, that's why. If there are other errors, though, feel free to stop by. We'll pull the Scantron, we'll check it. If there's an error, we'll get you those points back. Otherwise, we'll start chapter 19 on thermodynamics tomorrow, and we'll see you then.